Hello, everybody. I have Stephen Sprague here with me, CEO of Rivetz, and he has been active in the blockchain space, technology space, since 2013. Rivetz completed an ICO in September of 2017 and is working to deliver advanced cybersecurity controls available to users. You've got the floor, sir.
Thank you very much.
Thank you.
Thank you. So thank you, everybody. It's been a fun, long day, so I hope you're completely saturated on blockchain. My mission is to dispel a few myths for you. And I want to start with a very simple picture, which is around the concept of decentralized cybersecurity. So you've heard stories about aspects of cybersecurity and how blockchains have all of these capabilities. And I want to put a little of question mark over some of that, because there's a challenge in this space. And one of the challenges is that while the blockchain is censorship proof, you know, we can run it anywhere in the world and we can't prevent somebody from getting access to it. You know, can get out of China with a VPN and do a transaction, and that it's trustless, that the chain doesn't have an administrator. That's actually a really cool thing, is that blockchains just run. There's nobody really in charge. And that it's an immutable ledger, and we all agree that the data written to a chain, you can look at it and you can verify that it's never changed. It's the ability for the internet to store a fact. There's a problem, though, and the problem is really wrapped around this fundamental question of, was the transaction intended? If all I have is a chain, I can't prove that someone didn't borrow my private key. So we know the transaction happened, we know it was signed by a private key, but on chain, I have no evidence as to whether my private key was operated by me, operated by the Russians, operated by the 400-pound guy in Detroit. You know, you can pick your hacker in the world. So we propose a simple solution to this problem. It's at the heart of this is that we have keys and instructions, and we're creating keys and instructions. And by the way, this is not unique to blockchain. We do the same thing in IoT. We tend to do the same thing with nuclear missile launches, too. You know, we have like a suitcase. Inside the suitcase, we create an instruction. We send it over a public network to a silo, and then hopefully some dude in a silo looks at the message and checks the signatures before he processes the information in the silo. Basically, a silo is a very simple smart contract. And I want to preface this by saying, just think of this as the sort of Red October version of actually how sort of nuclear messages work. But you can think of it as secure message. We don't trust the network. The network is air. We send it over a radio. Anyone can listen. So what we're proposing is, how do we add to the blockchain this concept of a second key? And a second key that incorporates a health and integrity snapshot of the thing that sent the transaction. So that ultimately on chain, I can now have a piece of evidentiary proof that with just the chain, I can look at the chain, I can say, this thing in this condition with these controls sent this transaction. Now the good news is we anticipated blockchain way back in the late 90s, and a group of us got together and started an industry standards body called the Trusted Computing Group, and we're at like, depends on who you count, but today there are probably about 2 billion PCs that have shipped with hardware security technology on them, somewhere around 1 billion to 1.5 billion mobile phones. And so there's infrastructure already in place. You've experienced this. Things like Apple Pay use trusted computing, things like Samsung Pay or Samsung Knox. There's technology in many of the different PCs from different vendors in the marketplace, and it's industry standard capabilities that are there. And so we propose, how do you take this technology, you wrap it around the process of creation and formation of rules? Oh, kind of like a Trezor. A Trezor is a trusted computing device. It's a secure device in which we actually can form an instruction. And in that process, let's take a snapshot so we know that it's a real Trezor. Like if you get a Trezor and you ordered it off eBay and has somebody else's firmware in it, like what's it doing? I don't know. That's a problem. You want to make sure that it's really a real Trezor, that it actually came from Trezor. And so the same thing is true on all of this ecosystem. How do I know the transaction sent was the transaction I intended? And so if we add a second hash to the chain, and this is actually a transaction that Rivetz did a pilot of back a year and a half ago, and we have a video of it up on our website. You can go look at it. It's kind of a little grainy video. But it actually shows an attestation test as part of a blockchain transaction. Probably the most secure financial transaction ever done. because we actually measured and integrated into the proof of the certificate of the execution of the transaction, proof of the health and integrity of the device. So what are rules? Because now we can enforce rules in these devices that are enforced by a trusted execution environment. Simple things like PIN numbers and biometrics and passwords. Did you use a PIN number? Was a biometric in place when you processed this transaction? Was the transaction in an execution environment that was verified? We could have external controls. You know, a really good external control is you could have your device, let's say, call mom's device, and you can only do a Bitcoin transaction over $1,000 after 10 o'clock at night if mom says yes. By this way, great, because mom will get a phone call saying, hey, mom, you got to push the button on the phone because I'm doing this transaction, and you know, this will improve your relationships with your mother. And so we're trying to figure out then the economic model, because if we have all these external controls like geolocation or beacons or many other services, how do we pay for them? And so when you look at the core of what Rivetz does, actually our token, and I won't spend a lot of time talking about our core business, but our token is about how we compensate for those cybersecurity controls. So how does a device have a source of funds that it can spend on specific controls, then have those controls as part of the transactions? By the way, don't care if this is for blockchain. Do this for cloud authentication, for an IoT instruction. Before I open the dam valves on the dam and let the water out, maybe we should check and see if it's coming from a control system that's actually near the dam and not from Russia. Or again, pick your favorite location of choice where somebody can send instructions. Today, we function in a world that has known users with unknown compute. And unknown compute is very dangerous in blockchain because it's the thing that forms the instructions. If you don't know what computer is sending the instructions, guess what? We have no idea what instruction was being sent. Why is this important? Why should anybody care? If you're doing a project or an ICO or a token or something on blockchain, the data is fake news. If you can improve the quality of the data that's on the chain, we can increase the value of the data on the chain. If we can increase the value on the data in the chain, then everybody's project value goes up. So fundamentally, we have a really cool thing. We have an immutable ledger. Let's assure that the data on the chain is the data that we intend, and then we can prove the quality of it. It's never an absolute. It's just that these are the things we checked in order for that data to be what we expect it to be. So what is trusted execution? Trusted execution is a set of industry standards. It's embedded within the chipsets of your devices, and it's the ability for the device, independent of the operating system, to store and process code. And there are multiple ones of them. Like in a phone, your SIM module is basically a trusted execution environment. Your processor has something called ARM Trust Zone in it, which is a trusted execution environment. Intel's SGX is a trusted execution environment. So they're kind of everywhere. So yeah, we could make a Bitcoin wallet and 700 million handsets that would have an equivalent quality to a hardware Trezor device, just standard in your phone. So are we ready for that? It's kind of an interesting question as to, you know, if we showed up with 700 million hardware wallets, would the blockchain stand up? Based on the time it takes us to do an Ethereum transaction right now, that's like 700 million kitties. Like, that would be fantastic, right? We're at, what, only like 14 or 15 million wallets out there today? And so this is about driving industry standards to help that process. A simple thought. Trusted computing, in its most generic definition, operates tokens. Tokens operate chains. If you don't have trusted computing operating your tokens, then you don't know what you did. You have to have some sort of measured compute that helps you in the process of assuring that the thing that told your token what to do did what you wanted it to do, because it's a computer. It might lie to you. There are lots of capabilities. So if you look at a Samsung phone today, it supports trusted display. You can actually have the trusted computing environment write stuff on the screen independent of the OS. It has trusted input. I can put a PIN number or an address in that can't be altered. It has lots of different capabilities. So these technologies have been around for a while. I thought it would be useful to explain just the anatomy of a transaction. We all talk about transactions. We all have transactions. We use them every day. But we think that all transactions are equal. If you think of e-commerce, we really, really suck at e-commerce. We actually haven't done a secure e-commerce transaction. There are like 2 billion smart cards in Europe. You know what you can't do with your smart card? E-commerce. Well, it's only been 25 years, so they'll get around to it eventually, right? But you can't take that chip card, plug it in the side of your laptop, even though it has a smart card slot in your laptop, and do a transaction. Why? Because it's missing all the parts. You can thank the US Defense Department for that, because they built an identity solution around smart cards and they forgot all the parts too. So here's what you need. Trusted display. What you see on your screen is what you sign. Where do you find this? At Walmart. You go to Walmart, and on that little payment terminal, there's a little screen, and when you're checking out, it says $79.83, Walmart. And you say, oh, that's how much I spent. Don't trust the cash register, it can lie to you. But the point of sale terminal actually has a trusted display, a measured display. Trusted input. Now, you're supposed to type a PIN number into that silly little point of sale terminal. We're Americans, so you don't have that experience. We actually just have signatures. Nobody checks the signature. You know, sign the Grinch, sign whatever you like. Nobody checks. Sometimes you get a teller who's like paying attention, like looks at the back of your card, but actually nobody checks. But this is how you collect intent. Trusted execution. So we're all kind of familiar with this. This is the actual chip card in your wallet that you carry around, has the secret inside that chip, and actually forms the instruction of a transaction inside that chip. But then there's the fourth piece, and we kind of forget about the fourth piece. The fourth piece is some form of attestation that the other three pieces are working correctly. Because if I don't check it, how do I know that the thing is functioning the way I expect it to be? And so this, fortunately, has been designed for the last many 20 years plus now, using the concept of basically a Merkle tree and a hash in your device. So when I walked into my first real sort of serious Bitcoin conference, the Miami Bitcoin conference in 2014, I was like, oh my God, I've been looking for one of these. We'd shipped hundreds of millions of trusted computing devices, and finally we have a place to store the evidence that the devices are operating the way we expect them to. So this is a little bit of a messy picture, but it tries to show a simple concept. So today in cybersecurity, what we do in banking is we set up video cameras everywhere on the internet. We store all your bits, we store your keystrokes, we store your traffic, we look at you, we watch you, we look at the packets going in and out, we try and figure out what country you're in. We track every piece of information that's possible to collect, and then we compute a risk score to determine whether or not you are socially acceptably doing a transaction today. And by the way, if we could decide whether you've been drinking or not, that'd be even better if we could include that in the risk score. What we actually would like to happen in blockchain, because by the way, blockchain is censorship proof, so I can't use network security to assure the integrity of the transaction, because network security is by its nature censorship. I block things, I put up a firewall. So how are we going to do this? So on a decentralized basis, our opinion is that the device, the trust agent in your device, should be able to go out to external services and say, hey, tell me about myself. Am I feeling good today? Am I in the right location? Am I within the policy controls that my owner has set that says I should be allowed to do a transaction? And if I am, then let my transaction advance. And so we think the device plays a very important role. First, I know the integrity of the device, and they ask the device to check a series of controls, combine those together, and now I can put evidence on the chain that a known device in a known condition with a known set of controls produced a transaction. This is about creating a proof. Take any project you're looking at, take the claim that they're making, and then step back for a second from that claim and say, cool, how do I know that? Like, how do I know the person's passport is on the chain? Who put it on the chain? Well, if somebody stole a key that can put an attribute for an identity on a chain, then the person who stole the key can put an attribute on the chain. That's an interesting challenge. So when it comes to actually proving something, this goes to the quality of the data, you actually have to be able to form the proof. So just step back and look and say, cool, I just made a statement about what my chain project can do. Tell me whether you have the evidence to do that, or do you need the Windows log files? Because you might need the Windows log files to prove the thing that says your key wasn't stolen. And certainly, if I told you that the future of all blockchain security was getting your Windows log files straight, that wouldn't go over well here, right? We're trying to do this on chain, but we haven't put the evidence on chain to help us to secure that process. So the idea of a token as a new economic model for delivery of service, this is a really interesting challenge. This is about building utility. This is how services are paid for by a device. This is not a security. This is the tools for which we are going to conduct commerce and conduct business back and forth so that devices can pay for the services that they need. A device needs an allowance, and that allowance needs to run within a policy fence that the owner controls, so your device only spends money on the things you authorize. So at the end of the day, it's about high assurance instructions. A known user on a known device in a known condition, producing the instruction you intend. And if we can have chains recording instructions you intend, and we can provide the evidentiary proof that this was true intent, then we've accomplished our purpose. Thank you very much.